Welcome to clickmyproject.com. Let us discuss about a flexible fully hardware CABC encoder for UHDTV H.264/AVC high profile video. Selective video encryption provides low encryption time by selection of sensible bits from the video codec, which is well suited for real-time applications like TV, video conferencing, video telephony, video conferencing, etc. During AVC encoding, such sensitive data as NESets in CAVLC, intra-prediction slice and motion vector are encrypted. Perceptual encryption requires that quality of visual data is only partially degraded by encryption. That is, the encrypted multimedia data are still partially perceptible after encryption. This encryption technique was made in our proposed FPGA architecture. In this paper, we implement a CABC video encryption process for UHDTV 7680x4320 resolution. Experimental result shows that the performance level of our proposed system. The parallel binarizer and context modeler BCM and multi-symbol binary arithmetic coder MSBAC is coupled together by a variable throughput buffer and packets for throughput matching. Syntax elements are analyzed thoroughly and various SES processing engines are proposed to achieve parallelism for performance with high degree of flexibility for CABC designers. Special antennas have been paid to the feeding of SEs into BCM that is not discussed in most other works. Without the buffer-free access control and the buffer-free feeding of SEs, the high throughput of BCM and MSBAC engine will not be possible to integrate with the rest of the encoder engine. Otherwise, external preprocessing has to be applied for SEs feeding. Flexibilities of architecture and level of parallelism are incorporated into a CABC auto-generating scheme that can produce the CABC configuration according to user requirements. Towards a 1.13 micrometer CMOS technology, the highest performance design generated by the automatic generation scheme can encode 4.86 pins per cycle on the average, and it provides a throughput of 1234 megabits per second. The proposed CABC encoder architecture has been integrated into a H.264x AVC encoder of multimedia SoC successfully. This is the flow of our project. It consists of 6 modules: initialization, frame conversion, arithmetic decoder, packer, MP pipeline engine and encoder buffer. In initialization step, some application create collection of image related by time, such as frames in a movie, or by a spatial location such as magnetic resonance imaging (MRI) slices. These collection of images are referred to by a variety of names such as image sequences, image stacks or videos. The toolbox represents image sequences as 4-dimensional array, where each separate image is called a frame. All frames are the same size and the frames are concatenated along the 4th dimension. MMRead function will be used for loading and showing the input video sequence. The next block is frame conversion. The loaded video sequence should be converted into number of frames, that is still images, using MMReader function. To read video information, we using the read function, which reads the total information about the given video file. Then these image frames are converted into text file and load it in VHDL code by using read and write command in VHDL. Next block is arithmetic decoder. In this model, we first extract the pixels of image and then this was passed to binarization block. In that, it first converts the pixel value into binary bit stream. Then this was passed to coder block, which encodes the pixel data. Then this was multiplexed and passes to VTBAB packer. For each inserting bit streams, this was counted by state counter. Each state was saved in context memory, which saves the detail of each encoding bit state. The next block is packer. Traditionally, the GPU has been used almost exclusively for floating point operations, because integer operations could only be done using the mantissa of floats. Thus, processes that require bitwise logical operations were impossible. Another issue was that we have to render the output of the GPU to textures of pixel buffer before we could get to our results. This transfers the encoded bits to the system by using this buffer and packet for data transmission. The next block is MP pipeline engine. The prediction procedure, in which only ME was involved before, includes integer ME, IME, fractional ME, FME, And intra prediction, intra IME stage has the highest computational complexity in the encoding system. It must be highly parallelized to support the functions of variable block sizes and the multiple reference frames and to meet the real-time requirement. Unlike traditional mode decision algorithm, the Lagrangian mode decision is done after FME for all kinds of block sizes and reference frames, which improves the PSNR by 0.5 to 2 decibel. However, a large increase in the computational complexity and complex sequential flow are demanded. The next block is encoder buffer. Finally, the encoder bits are converted into decimal and save it as a file. Finally, this was converted to text file and made the MATLAB tool to read it and display the binary frames. Open the source code folder and select main.m file and right click on it and select run file. Select input a video from these two videos. I select the second video. This is the one image of the one frame of the input video. Please wait a moment and the coding will be executed very soon. Here figure 6 shows the videos number of videos versus the throughput value. Compared to existing system, our proposed system achieves high throughput, and figure 4 shows the compression ratio of our proposed system is higher than the existing method. And here I displayed the BER and throughput values of our proposed system. From this I conclude that compared to existing system, our proposed system achieves high throughput and compression ratio than the existing one. Thank you.